Welcome back to Honors Calculus. In this video, we're looking at further problem solving with optimization. We've looked at some optimization problems already. We've seen the basic process. The extra thing that I want to look at in this video is situations that call additional constraints into the problem. And so without further ado, let me get my head out of the way and let's dive right in. In this problem, I'm going to look at building a pen, although I'm going to build a pen in a very interesting bit of ground. Right. We have already got a building on a piece of property, and so we don't have to worry about building anything on that wall. And we want to come out, come up, and come back in order to construct a pen. So we need to build 3 walls of the pen. But there's some issues. It turns out that the particular piece of land that we are building on, the northern part of the wall is relatively simple to work with. It's going to cost us $10 per foot to build the northern wall of the pen. The eastern wall and the southern wall are in some very rocky terrain. And so it's going to be a lot more work to set up a foundation that will hold the pen. The southern wall is going to cost us $15 per foot, and the eastern wall is going to cost us $25 per foot. All right. Key constraints here. I want this pen to be rectangular. And I can afford to spend $7,000 on this project. So with those constraints in mind, the question then is, what are the dimensions of the largest pen that I can build? All right, so to solve this problem, we need to introduce some variables. We need a length and a width of the pen. We could use L and W. That seems a very geometric thing to do. But since this is calculus, I'm going to call those dimensions X and Y. And of course, we know that the area of the pen is the length times the width, X times Y in this case. We also know that the cost of this pen is being constrained. For X, I am limited building this wall, which costs $15 per foot. So if X is in feet, that means that that wall is going to cost 15X. This wall is going to cost 25Y. This wall is going to cost 10X. And then the last wall is going to cost nothing because the building is already there. All right, conveniently simplify that. We get 25X plus 25Y. And we know that the total cost has to be less than or equal to $7,000. Getting as close as we can to equal to seems like a good idea here, right? The more money you're spending, the more fencing you're getting, the more fencing you're getting, the bigger you can make this thing. But we know it has to be less than or equal to 7,000. All right, so we have our object function, a equals x times y. That's the thing that we want to maximize. We have a constraint, 25x plus 25y is less than or equal to 7,000. Hopefully we can do something with this. The setup in this particular problem is relatively nice to us. I can take this inequality and divide both sides of it by 25 to get that x plus y is less than or equal to 280, which means that, solve for y, why not? Y is less than or equal to 280 minus x. Taking that constraint, I can put it into my object function. A is equal to x times y, which we're now constraining to 280 minus x. We can multiply that out, and then we can differentiate, because we're looking to maximize a. And in order to maximize a, we want to find the derivative. The maximum must occur at a critical value. So we take that derivative, we set it equal to 0. And we get actually a relatively straightforward solution. X is 140. And plug that in here, we get that y is 280 minus 140, which is also 140. All right, so when you think about these kinds of problems, I'm sure that you've seen in previous mathematics courses that if you want to draw a square that has the largest, or a rectangle that has the largest area for the perimeter, you draw a perfect square. Given that one side is already constrained, very often there are other ideas that can come up that will make it so that the dimensions are a little bit different. Add in that cost factor, and in this particular problem, we ended up back at a square again. That doesn't always happen. That's a fluke of the particular numbers that we were looking at. Regardless, the thing we are studying here is that we have our constraints that are not directly related to the object function, but give us some control over how we're solving things. And applying those constraints, turning this into a system of equations or inequalities and going from there is the big idea that we want to focus on with this. All right, so with all that said, let's go on to one for you to try. And so on this one, I want you to think about standing on a shore. All right, so we've got water here. All right, it is water. Sometimes I use that hash to mean this is a solid wall you can't get past. This is water, you can get past it. You are currently here. You want to be there. All right. So you are going to, well, swim. You're going to dive into the ocean and you're going to swim from where you are to the island that you want to get to. There, we'll put a little lighthouse on the island. I guess can't quite tell it's a lighthouse because the top cut off, but yeah, there's a lighthouse on the island. All right, so you could just dive in and start swimming right away. Or you could take a path that takes you along the shore for a while and then go in. Because, as it turns out, most people have a running speed and a swimming speed that are not the same. Let's say that you have a running speed of 6 miles per hour and a swimming speed of 3 miles per hour. All right, your running speed and your swimming speed are not the same thing. And let's say that the distance across the land from you to where this lighthouse is 4 miles. And the distance directly to the nearest shore from the lighthouse is 2 miles. So the question is, how far do you want to run first before you dive into the ocean to swim the rest of the way? All right, let's walk through that whole thing one more time. If I take a step over here, hopefully we can still see the picture. All right, so you are standing on the beach. There is an island somewhere in the ocean. That island, if you walk 4 miles along the beach and then swim 2 miles straight line shortest path, gets you to the island. In order to get from where you are to the island, you could dive into the ocean right away and swim straight across, or you could run across the beach for a little while first and then dive into the ocean and swim the rest of the way. So, given that your running speed is 6 miles per hour, your swimming speed is only 3 miles per hour. The question is, how far do you want to run first before you dive in to optimize your swimming speed? So I want you to take some time, think about this problem and how to set it up. See what you can do with that, and I'll see you in the next video.